introduction. That's probably the best introduction I ever got. So thanks very much for having me. As the host introduced, my name is Tanvir Hussain. I'm a professor of coatings and surface engineering. So the talk I'm trying to give today is about innovation in thermal spray and cold spray. So basically, we're looking at two things. One is, how do you build ceramics from a liquid feedstock or raw materials? And how do you make metallic systems without melting? So I'm aiming to finish the talk within 45 minutes, and hopefully that will leave me a little bit of time for question and answer. I'm also an EPSRC fellow, as the host has kindly mentioned. So basically, what is coatings? So the first way to think about it is, if you look around us, almost everything is coated with something. And the simplest example is probably paint. And the paint you have got on the wall, and also you have got paint on the furniture. The simplest use is decorative, or to prevent it from corrosion and rust and things like that. Similarly, in a plane engine, which is the core focus of this talk today, is everything is coated with something. So I've got a couple of samples in front of me. So this one is a high pressure turbine blade from a Trent 900 engine. So it's a air cooled turbine blade, nickel-based superalloys, and it has got a very fine white coating on top. And that white coating is as thin as my hair, so 100 micron roughly. And what it does, it drops the temperature by 100 degrees Celsius. That's equivalent to taking an ice cube out of the freezer, putting in the oven, crank the heat up to 200 degrees Celsius, and you expect it not to melt. That's what we're doing. And these coatings are essential in our engine operation. So that's from an X engine component, and that's a nozzle guide vane. So you can see that discoloration because it had quite a few hours of service. Similar sort of systems. I also have got another nice and shiny one, which is titanium nitride here. And this one is an erosion protection coating on top of a compressor blade. So let's make a start then. So the coatings market, specifically the thermal spray coating market globally, is expected to go from around 9 billion to 13.7 billion by 2023. So the compound rate we're talking about is 6.7%. Examples of coatings: the afterburner, gas turbines, the space rockets, also your automotive engines, they're coated. The exhaust manifolds, these are also coated. We also have got cold spray coatings, which are on copper-based systems, which doesn't oxidize when you're depositing because it's a cold system, and also making net shape manufacturing components like this. This is a paper roller. Paper roller industry needs a very hard wear-resistant coating for paper and printing application. And also when we go through hip replacement, knee replacement, or anything which goes inside our body, those components are also coated with a bioactive coating, either with titanium or hydroxyapatite. So the coatings are almost everywhere. In the UK, the coating sector is 11 billion, and it plays a key role in products over 140 billion. In terms of gas turbines, we have got an impressive production of around 228,000 aviation gas turbines, and the market value for that is around 1.2 trillion. So the numbers give you some idea of how significant the coatings is for operation of these components. A little bit of history, because I guess not everyone is familiar with thermal spray. So thermal spray was first developed in 1910 in Switzerland by an inventor called Dr. Schub. And what he noticed at the time, his son was playing with a toy cannon, and he was playing with lead in that cannon. And when the cannon ejected lead, it hit the surface and it deformed and stick to each other. And that's how a coating was developed. So that's Dr. Schub with his pistol spraying of metal at the time, demonstrating on a component. And those are from his patent nearly 100 years ago. From that point onward, the technology developed quite a bit. There are three key technologies we need to know a little bit about before we can start going into the details of things. For thermal and cold spray coating folks, the temperature versus velocity diagram is quite a useful one. We're going to talk about plasma spray. plasma is incredibly hot as a system. And here we're talking about 10,000 degrees Celsius. So similar to the surface of the sun. In a plasma spray, you have a tungsten cathode and a copper anode, and we are injecting a plasma gas. And within that plasma, we are then injecting a powder, and that powder particle is melted. That's then accelerating and hitting the substrate to form a coating. So the key thing about plasma is it's really hot. Particles are traveling slower here. In high velocity oxyfuel or HVF, it's like a small rocket engine. And what HVF does, you have oxygen and kerosene or hydrogen coming in, and it produces a supersonic combustion. So if someone looks into the HVF flame, they would be able to see the shock diamonds coming in. And in that supersonic flame, we inject powder or suspension. These particles accelerate, get molten, hits the substrate, and develops a coating. So HVF tends to be velocity-wise traveling between 500 to thousands meters per second, much faster, but temperature-wise much cooler than plasma. And the other end of the technology, we have got something called cold spray. So cold spray was first invented in 1990s in Russia. And at the time, people were experimenting with particles in a supersonic wind tunnel. And what they noticed is if the particles travel fast enough, instead of eroding the surface, it actually deforms and sticks to each other and it forms a coating. And so the industry has developed quite significantly. Here, we have got a D-level nozzle or a convergent divergent nozzle where we're injecting powder particle. No heat is coming, and the reason it's called cold spray, we're not melting anything here. These particles are then hitting the substrate, deforming at a high strain rate. So we are talking about strain rates of 10 to the power 6 to 10 to the power 9 per second. And that then forming a coating, and that can also be for additive manufacturing or net shape manufacturing. Historical development, there are three things I talked about. So that was 1910 when things started. HVF came in 80s, and that technology kept developing. And then cold spray commercially started becoming available in 2000. One of the big changes happened to the sector was cold spray becoming a lot more usable. So there are over 30 or 40 research groups working on cold spray. And another new technology came in, which was called ceramic suspension spray or suspension plasma spray. All the things I've talked about so far uses powder. What nanofeed and nanoceramic, it's a bespoke system from MedTech in Canada. What that allowed us to do is injecting fine particle or particulates less than 5 micrometer. When particles are less than 5 micrometer, you can't easily feed it using a conventional powder feeder, so you need special equipment. And the talk is going to cover a little bit of suspension, plasma spray, and a little bit on cold spray. In Nottingham, coatings and surface teams, we work with thermal spray, suspension, cold spray. We also have got a couple of lasers. We do testing in tribology and wear, room temperature all the way to 1000 degrees Celsius. We do thermal cyclic testing, burn rate testing, and also hot corrosion, which is a deposit-induced corrosion for type 1 and type 2. Mechanical systems are geared for testing these coatings under creep, under fatigue, or 4-point bend testing. And we have the standard characterization equipment with electron microscopy and other types of spectroscopy. This is a quick slide to show where our research sort of thrust comes from. Where we focus on is the processing, microstructure, properties, and performance relationship. So processing side of things, we have got a whole range of technologies available. We use those to process it. We study their microstructure, and then we measure the properties. This is an example of macro-intrusion porosimeter, where we are measuring the porosity within the coatings. And then we test them in simulated environment. What would happen to these coatings in real life? And then we go back to the cycle and design the processing window to get the desired performance that we want. So let's start with suspension plasma spray. The host kindly mentioned about the EPSRC fellowship. So I'm an EPSRC fellow. In the EPSRC fellowship, what I'm looking at is designing and developing new composition using the suspension plasma spray, which is UK's only suspension plasma spray at the moment, to cut the material's discovery to demonstration cycle. In our field, to design a powder and to get that powder into a coating can take over a decade. What we're trying to do here is come up with composition backed up by machine learning and artificial intelligence algorithm and turn those compositions relatively quickly into a coating. So the idea is we try a lot more compositions and we fail fast and we learn from our failures. That's how the coating center looks like. So we've got a center of excellence in coatings. This is our high velocity oxyfuel or HVF booth. This is our plasma spray booth, and that's our cold spray booth. All of the control systems are outside the booth. All of things are on wheels. We can essentially connect things up, spray, and then move things away. We also have got diagnostic kits, which can look into a plasma or a supersonic combustor and measure particles velocity and temperature. All of these have got a robot inside, so it's an entirely robotic manipulation system, similar sort of equipment what you'd find in industry. This is probably the largest thermal cold spray research center in the UK at the moment, to my knowledge. So what we have invested recently is in a system called axial injection plasma spray. So that's the plasma spray booth, and you can see the robot here and the control system outside. It is quite a significant power supply system, which requires 750 ampere. We had to put in a new power supply from the electric substation to our building to cover that. And that's the plasma spray torch that we have installed this year, which was part of the infrastructure development and part of the fellowship as well. It's essentially 3 torches in one, and it can operate up to 150 kilowatts. So it's quite a big system. And essentially inside, it has got 3 cathode torch, which means it can take on a lot more challenging ceramic composition, which was not possible to use before. Plasma spray, I give you a little bit of an introduction on the slide, couple of slides before. In a plasma spray, we have an insulated housing. We have the electrical connections, and we have got tungsten cathode, we have got an anode, and we have a plasma here. And in that plasma, we are injecting powder, which is carried by a carrier gas. These powder particles are accelerating towards the substrate, hitting the substrate, and then we're getting a coating on there. What the suspension plasma does, and axial, instead of doing things radially, it injects things axially, which comes with its own processing challenges. And instead of using powder, a typical plasma spray powder is around 5 to, let's say, 100 micron, whereas the suspension system operates with particles of 10 nanometer to 5 micron. So it's operating in a very sub-micron to a nanoparticle range. And this is how the cycle looks like. We start with a submicron or nanoparticle. We turn them into a suspension, and there are commercial companies who will make this suspension, small quantity of suspension we can make ourselves, goes through a suspension feeder and a plasma processing, and it results in a coating. I will be showing you quite a lot of scanning electron microscope images of coating. So that's the bit of the coating onto a substrate, just to show that it's a relatively dense coating, well adhered to the substrate. So the concept here is with the axial one, we're injecting the suspension axially. There are some systems traditionally used to inject it radially, but the challenge with radial injection and suspension is these suspensions of the powders can overshoot or undershoot the plasma. And as a consequence, a lot of these particles could be outside the hot zone of the plasma. As a consequence, you have got a sustainability issue. A lot of the particles may not deposit and contribute to making these thermal barrier type coatings we're talking about here. Application wise, Axial 3 is the name of the plasma that we have. Aluminium silicon, abradable coatings. When these turbine blades are operating at 10,000 RPM, it has got a fin on the top end, and it needs to cut against a seal. So it produces a gas tight seal. And those are made out of aluminium silicon with polymer. So abradable seals are made from this type of plasma. In the afterburner, we need a chromium carbide with a nickel chrome system for high temperature application. Again, can be done using this plasma. In the hot section of the turbine, we have got wear-resistant coating like alumina. We can use that. And also the thermal barrier coating. I will cover that in a bit more detail, which is in the hot section. That's also one of the primary application of a suspension plasma system. More examples, what the axial plasma can do, it can produce multi-layered structure. So this one is a gadolinium zirconate structure over yttrium-stabilized zirconia, and that's an M-Crowley bond coat, and underneath that nickel-based superalloy. So all of these are a multi-layered system. Similarly, it can also produce alumina in a much denser sort of alumina. For solid oxide fuel cell guys, it can produce electrolyte, which is much denser, and also porous anode, where you want porosity. Whole ranges of application from functional coatings of yttria as well as alumina. And wear resistance is quite an interesting application for coatings because friction and wear are significantly energy consuming. If you think of any transmission system, when two surfaces are rubbing against each other, if you can reduce the coefficient of friction, you can save quite a bit of energy loss, transmission loss in that sense. That can be done using the same plasma. The reason it became so popular is in the conventional engine, the one I'm holding at the moment, this is the state of the art. We have got a bond coat. On top of that bond coat, we have got a thermally grown oxide or TGO, which is an alumina. Then on top of that, we have a Bart's feather-like columnar structure called EBPVD coated thermal barrier coating. And EBPVD, this Bart's feather-like coating, are quite desirable. That means at high temperature, they can expand. And when they're cooled down, when the engine is cooling down, they can contract. So essentially, they are highly strain tolerant. But the problem is the EBPVD systems are quite expensive. The sort of systems we have in this country, around 13 million we're talking about. And the process is quite slow because we're talking about layer by layer deposition of atoms here. What that suspension plasma is aiming, so this is a conventional plasma spray coating. It has got lower thermal conductivity because it has got more porosities or holes in it compared to the state-of-the-art electron beam PVD. But in strain tolerance point of view, this one is worse because it can't really expand or contract that easily. What the suspension plasma can do, it can produce this Bart's feather-like structure, sometimes also called cauliflower type structure, using a plasma at a fraction of the cost. So SPS systems installation-wise, we're probably talking about around 500,000, no more than that, versus 13 million. And the reason it produces the columnar structure, those fine nanoparticles that we have tends to follow the plasma jet stream. And when you have got asperities on the substrate, those particles travel along that plasma, hits those asperities, and starts depositing and producing that column. So just by altering the particle size, you can alter the microstructure that we get, which is highly desirable. Moving on to the other systems of HVF, which is high velocity oxyfuel, I will give you a range of sort of case studies to get a flavor of what the suspension and solution precursor systems can do, and with some real life application. What we have used to produce this, that's our high velocity oxyfuel or HVF torch. It has got a bespoke nozzle in front of it as a shroud. And this Techna system looks into the flame and it can pick up particles, velocity, and temperature. We can inject suspension axially as well as radially. For oxygen sensitive systems, radial injection is much preferable. We have a suspension feeder, which was originally developed at Fraunhofer, but then we modified it to have a closed loop system with pressure control. So we can control the amount of liquid being injected. And here you can see with some imaging technique, how we inject the liquid, what happens to it, and how it breaks out. Similarly, to the suspension plasma, we start with powder particles, convert into a suspension, goes through a suspension feeder, and gets injected axially in the flame torch. So we're going to first focus on thermal barrier coatings. Thermal barrier coatings, this particular one, this was Harry's work. As you probably realize, I don't spend a lot of time in the labs anymore. So there are lots of researchers working and developing. And as I go through the presentation, I'll try to introduce them. So Harry was looking into A stands for aqueous and E stands for ethanol, medium of suspension, which is YSZ, yttrium-stabilized zirconia. And he was working with 400 nanometer, 7 to 8% YSZ, and the top surface of the coating, that's how it looks like. And you can see the splat size, which is the building block of coatings, are different. And that's down to the surface tension. And when you're injecting water into a HVF torch, you're essentially cooling it down. And because of the surface tension, the particle droplet tends to be bigger. With ethanol, you're adding more fuel to it, so you are adding more heat, but because of the surface tension of the droplets, they tend to be smaller. So it produces different types of microstructure in the coating, and that was in this particular paper we were exploring the effect of suspension medium. That's Daniel, who's in his final year PhD studies. So what Daniel did, all of these coatings have got porosity, and porosity is not a bad thing in all coatings. Some cases, porosities are highly desirable. And because the porosities allows us to have lower thermal conductivities. So Daniel was using neutron beam in Unsto in Australia and using neutron scattering to measure intensity over a Q vector to understand the porosity within the coating. Because of the nature of these coatings, they are nano sort of ranges. It's very difficult to measure the porosity using conventional techniques. So these are the two commercial companies that supply suspension at the moment, Tribeca in Austria and Oerlikon is an international company based in Switzerland. What we're doing, we are measuring the porosity with different levels of heat treatment using a scanning electron microscope in both cases. And we're also measuring the porosity using small angle neutron scattering or ultra small angle neutron scattering, SUNS. And we are trying to develop a model here because we all have access to an SEM. Not everyone have access to neutron diffraction facilities or neutron scattering. So the idea is if you can develop a model which can correlate the true porosity using advanced techniques by doing things on an optical microscope or in a scanning electron microscope, would be able to predict what's the true level of porosity in there. Moving on to other systems. If you remember in 2010, when the Icelandic volcano erupted, I can't even pronounce the name properly, Yavaskula, the entire flight over Europe came to a grinding halt because the CMAS or calcium, magnesium, alumina silicate is highly aggressive to the thermal barrier coating that we have. So last 10 years of research has gone into coming up with new compositions which can prevent the CMAS attack. So here, Leng is a PhD student at the moment. Leng is developing solution precursor gadolinium zirconate, a very dense coating over a suspension spread YSZ to see how would they perform under thermal cycling and in CMAS condition. Solution precursor, we'll talk about it a little bit later. So in the suspension spray, we have got a particle in a liquid suspended, but in solution precursor, instead of that, we start with a precursor salt. There is no particle in there. And that precursor solution decomposes through the flame and ends up getting into a solid coating at the end. So you bypass this whole route of making powder and then suspending the powder in a liquid and getting a coating. You go from a salt solution directly to a coating. So it produces quite different types of microstructure. And we were examining how they compare a double layered system against a single layer system in a thermal cycle test, which is the most aggressive sort of testing that you can do. You heat things up at 1200 degrees Celsius, cool things down very rapidly and see how long it takes for 20% of the coating to fail. Similarly, we're working with yttrium aluminium garnet because YAG is another material which has got high temperature capability and it doesn't go through a phase change at the operating condition. So to make that YAG layer, we were using aluminum nitrate and yttrium nitrate salt. Tunji, who has already finished his PhD, and we were comparing how would a solution precursor YAG compared to a suspension YAG. So here, these are some fracture surface of these lamellas or the splats. You could see the splat microstructure from a suspension sprayed coating is quite different from a solution precursor sprayed coating. because the mechanisms they are going through and the degree of porosity that they develop are quite different as well. What we're interested in also thermal conductivity. So we have a laser flash thermal conductivity measurement kit. Typically, when we are working with the state-of-the-art sort of TBCs, we are operating around 1 watt per meter Kelvin. And what we found out, if we work with YAG and a solution precursor one, we can drop the thermal conductivity quite significantly, different scales, and that one is for thermal conductivity of suspension one. However, when it comes to thermal cycling, our solution precursor system tends to fail much faster than the suspension one. So there is always a trade-off here between better thermal conductivity versus better lifetime. So what happens in a solution precursor? I was giving you an example of YAG. So this is a solution precursor droplet in a flame. It goes through primary and secondary fragmentation. We have got a droplet. The droplet evaporates on the surface. We can see solid phase condensation, then precipitation, and then depending on the condition, it can go through, turn into a dense solid particle, could turn into a particle with a solid core, or agglomerated particles. These are the particles collected on a polished substrate to see the type of features that we get. And all of these are useful for us to develop a model so we understand how different types of precursor behaves. This one was done on niobium doped Titania. Moving on to more functional coatings of self-cleaning, hydrophobic or de-icing coatings. In aviation industry, trying to clean the wing surfaces or aerodynamic surfaces is quite a big challenge because when you have got wing fouling, you have to clean it, de-ice it properly before you can fly again. So we're working with a range of coatings which can solve that problem. So the first one was Titania. Titania, this is an anatase Titania and it's widely used. We're looking into coating cross-section at the top, and 40, 56, 72, 85, and 101 stands for the kilowatt of the flame. So we started with submicron titania. So these are the titania particles suspended in a suspension, and then we sprayed it under identical processing parameters, except we changed the flame power. And when we do that, we see the amount of anatase within this coating content start decreasing and the coating microstructure starts changing. We published that work in European Ceramic Society. That was our very sort of early days of work on suspension, but it taught us by optimizing the spray window, you could come up with very, very different types of microstructure and different phase content. Moving on to from anatase to rutile, we are still talking about titania, but this time we are using a rutile suspension sprayed at 40 kilowatt, 72 and 101. And as we see, the anatase content changes quite significantly depending on the flame power, but it's not linear change. That's one thing it's worth remembering, because titania is really great because it can react with UV light and it can break down sort of surfaces for contamination, and it's also used as a self-cleaning coating. But the ratio of anatase to rutile is quite critical in these coatings, and there's a lot of study out there where the argument is still going on, what's the optimum anatase to rutile ratio? And that's what we're doing. We're measuring current density versus potential of these three coatings under artificial light to figure it out what would be an ideal composition here. Superhydrophobic, we were spraying ceria at the time, and we were spraying ceria onto aluminium, stainless steel, and nickel. And the sort of contact angle we were getting was around 146 to 150 degrees Celsius. You can see those nice water droplets. So the idea is, if you've got a ceramic coated substrate, the water will roll off, or even for ice phobic coatings, the ice crystals will not form. As a consequence, you can have a more robust coating, which can be superior to the polymeric coating that's currently used. That was Hafsa's work at the time. Moving on to more towards tribology and wear. In a plane engine, lots of components are rotating. And when there is rotation, there is friction, there is wear. So there is a significant interest from the propulsion industry is to reduce the transmission loss and reduce the level of wear. Here, this is the first time we worked with some cheap graphene particulates. We call these graphene nanoplatelets. So these are not single layer pristine graphene. These are 5 to 6 atomic layer thick, very, very cheap sort of graphene nanoplatelets. And we are adding 1 weight% with alumina, which was our base coating. And here you can see we rubbed an alumina ball against the coating without the graphene nanoplatelet. You can see the deep the scar is, and you can see the scar on the counter body, which is ball. And when you have got 1 weight% alumina, 1 weight% graphene nanoplatelet in the alumina, there is barely a scratch, and the spot on the alumina body is also quite small. And in the wear terms, we have got specific wear loss in millimeter cube over Newton meter log scale, and it drops by 2 orders of magnitude in that case. So there's a significant improvement in reduction of wear when you add something like 1 weight% graphene nanoplatelet as a reinforcement material. That was James's work at the time. We then went further and we tried to develop a system where we're injecting graphene nanoplatelet suspension directly in the flame. Because it's a carbon-based material, so it doesn't like high temperature. So when we inject it axially, it doesn't work very well. So we were playing with the distance at the time, moving from 10 millimeter all the way to 60 millimeter, and see when we inject that suspension, how it breaks up. We are working with different types of flame power, 25 kilowatt, 50 kilowatt, and 75 kilowatt. And we are also working with different types of flow rate of suspension to understand what condition is required to develop a GNP film on a surface. We did succeed in depositing a loosely bonded GNP film. And with that film, this is the coefficient of friction versus number of cycle. We can bring the coefficient of friction down to 0.1 here, compared to which is typically at 0.6. So it does work quite nicely as a self-lubricating material. Moving on to a bit more structured work. So here we were looking into what happens at an atomic level when you have got a dry sliding wear of these graphene nanoplatelet stacks. It tends to form a tribofilm, and that goes through an oxidation, and it forms cross-linking between these layers, eventually ending up with amorphization, turning into amorphous carbon. The coating does work up to a certain number of cycles when the film breaks down, and you can see the coefficient of friction is going up. Couple of TM images to show when we started with this, that's how the edges look like of the graphene nanoplatelet, which then amorphized and turned into a small round-shaped TM images of this carbon. That's Kerem's PhD. He's coming to his final year now. This is not suspension. This particular one, we are working with an Innovate UK project where we're looking into carbon nanotubes. So in industry, tungsten carbide cobalt powder is the most commonly used powder for coating deposition. And we were using carbon nanotubes and then spraying it. Carbon is a great material, but it doesn't like high temperature. So there's quite a lot of work which goes in trying to modify the feedstock in a way you can get them into a coating in a usable format. So what we're looking at is Raman spectroscopy. By looking at the DEG and 2D peaks, we can figure it out what's the level of CNT retention we have within the suspension, within the powder, within the coating, and after the wear testing. It's a published piece of work in Materials and Design. You can go and read it. Moving on to, I've shown you quite a few examples of where coatings can be used, but a lot of the underpinning science is from modeling, because we can't do experiments of everything. For example, inside a combustion chamber, there's no way to observe what happens inside a combustion chamber. But by using CFD, we can get around to that problem. So this is a CFD mesh. Sometimes we develop our own model in ANSYS Fluent and sometimes open source. These are the ones where mixed oxygen and hydrogen coming in. That's the central bit where we are injecting suspension. This was a multi-phase model where we have got a coupled volume of flow with DPM, the discrete particle modeling. And let's hope this video works for me. So what we're doing here, this is a combustion chamber where oxygen and hydrogen coming in and combusting. And at the center, we are injecting suspension. So that was Sunil's work, and that's velocity and that's temperature. You can see when we're injecting the suspension, how this turbulent environment is breaking down that suspension, because on this side, I have got the nozzle. All of these suspension particles are accelerating towards that nozzle and getting deposited on that end. Moving on to more sort of advanced work. Here we were looking into those suspensions that we're injecting, and we varied that in 3 different Weber numbers and 2 different time points to understand how does that liquid fragment. So far in our field, all the advanced CFD models that we have can't really predict the primary fragmentation very well. The part of this work was, can we develop CFD models working with my colleagues in CFD, which can tell us how these droplets form, which will then eventually turn into a coating. And you can see some really nice, interesting features, how the fragmentation occurs depending on different types of Weber number. Moving on to cold spray, I did promise to talk about a little bit of metal. So cold spray is widely used at the moment for repair technology. So this is a Seahawk intermediate gearbox, and it was repaired using cold spray. At the moment in aerospace industry, specifically for magnesium alloys and aluminium alloys, a lot of the components are thrown away because there is no way to repair it. What cold spray can do is it can repair the component and in a more sustainable manner. So repair, reuse, and recycling for the materials processing folks is becoming quite an interesting topic. So here we are working with high entropy alloy, so cobalt, chromium, iron, nickel, manganese. So John, who is still doing his PhD. So what happens in the cold spray? You have a particle hitting a substrate and at very high strain rate, and it forms a metal jet. That metal jet, the conventional theory was, removes the oxide, and as a consequence of removing the oxide layer, you form a metal-to-metal bonding. And the jet forms, here we are modeling different particle velocities going from 550 to 900 meters per second onto stainless steel 304 and Ti6Al4V. Some of the experimental images to show what happens when a spherical particle comes and hits the surface. And what happens in cold spray is the strain hardening, thermal softening dominates over strain hardening, and we can see a jump in strain. And by looking at which point the strain jumps, you can figure it out. What's the critical velocity required for particles to deposit to form bonding? So there is no melting taking place. All we are working with here is the velocity or the momentum of the particle. Moving on, some of the other works we were doing was on aluminium alloy. So this one is an aluminium 7000 series. And in aluminium 7000 series, that's an as received powder particle, and that's a solution heat treated one. One of the challenges of aluminium alloy, because these are precipitation hardenable alloys, when you repair it, you still have to do a heat treatment. And as soon as you do the heat treatment, you may lose the certification on that part. And these alloys are also very difficult to spray. So these are in as received powder. You can see a very thin layer of coating, lots of rebounding, lots of particle gaps bouncing back. And then I have got some solution heat treated powders. What we have done in solution heat treated, we have heated the powder at 450 degrees Celsius and then quenched it. And we essentially altered the microstructure of the powder. As a consequence, the particle tends to deform much better, forming these jets, more bonding, and we can see the coating under identical condition tends to be much more robust. Moving on to a little bit of the mechanism. So here we are working with 6000 series alloys, and that's my Euler image of the as received powder and the solution heat treated powder. Low angle grain boundaries are white lines, high angle grain boundaries are black lines. You can see there's a fair bit of low angle grain boundaries in the as received condition. So the conventional wisdom used to be gas atomized powders are dislocation free, not stress. That's not true anymore. As received, there's quite a lot of particle to particle interface issues there, as you can see with the cracks. So that's one particle, another particle, but they're not bonding very well. Compared to that, solution heat treated ones are forming much better. Band contrast images, you get a better pattern quality when it's a solution heat treated one, and it suggests the lower amount of lattice defects, which also exhibits a darker contrast due to a high number of grain boundaries. TM images, again, as received and solution heat treated, showing more close bonding at the interface between two particles. We then took this work a bit farther and tried to understand what's happening within these particles. So that's a as received particle. These two are inset high mag images. This is a solution heat treated particle coating and inset images. And we plotted distance versus misorientation in both cases. What we see, the heat treatment powder shows low angle grain boundaries mostly located at the particle-particle boundaries, whereas the heat treated powder shows interior containing a limited amount of low angle grain boundaries where particle-particle interface presents a wide distribution of low angle grain boundaries, which also suggests accumulation of lattice defects. So essentially, in the solution heat treatment powder, we are seeing more things happening at the interface as opposed to within the particle itself. Whereas in the as received condition, we are seeing lots of things happening within the particle as well as the boundaries. I think that's my last slide on technical stuff. As the host kindly pointed out, there are a little bit of things I would like to talk about, which is about scientists behind the science. So first of all, the reason it's important is because research funding is what dictates what science we can do, how we can recruit PhD students, how we can recruit postdoctoral staff, how our career advances and things. Couple of screenshots. This is from the EPSRC's large grant report on gender. The bit to point out here is as the size of the grant increases beyond 1.5 to 2.5 million, you start seeing a big disparity in funding between two genders here. So this one doesn't have non-binary, this one only has got male and female. And this is a systematic issue, and a systematic error in a system would be called bias. So you would argue that there is a bias within the system, which is leading to this problem. Similarly, leaky pipeline analogy, this is from Nature, Ecology and Evolution, which basically says women are less likely to be employed as grad students in male PA's lab, which is 70% of the labs at the moment. Unfortunately, they are half as likely to get external letters of recommendation. In US mostly, and North America, you get startup grants to start your lab, and that's how the tenure track positions start. There's a significant disparity between genders as well when it comes to startup grant. And also, the same trend continues when it talks about number of grants, number of papers, as the last author in our field. Last author usually means the head of the lab. And as a consequence, the senior positions. So that pipeline continues leaking. You can go and read the papers, and it presents a really nice picture of what the problem that we face. Similarly, in ethnicity side of things, this is from EPSRC's, which is my research council historic data. Only two groups here. You have got white and ethnic minority. 20% of EPSRC's remit is 20% of EPSRC's researchers are ethnic minority. Population-wise in the UK, we are talking about 15%. On average, the size of the grant is around 120K plus less. 120K roughly is around 1 year worth of postdoctoral time, equipments, consumables, and research time. So you can start to see the disparities in the system. Why should we care? I think that's the sort of message I want to leave everyone with. This is from McKinsey's report, and they looked into 350 plus organizations, and their finding was the companies in the top quartile for ethnic diversity have got a 35% more revenue. Companies in gender diversity in the top quartile have got 15% more, and companies who are in the top quartile for gender and ethnicity, they have got 25% more. So these are hard numbers coming from large organizations. So having the diversity within the scientific discipline and within the scientists is ultimately beneficial for everyone. And that helps us solve the global challenges, because if everyone thinks the same way, we're never going to be able to solve the big ones. Brings me to my last slide. So as you can see, all aerospace components, they require surface coatings to function. Cold spray is a really nice way of depositing metallic coating without melting. Suspension thermal spray is an emerging technique which can produce columnar type structure, which is really beneficial for thermal cycling point of view. Solution precursor is another new technique where you're using salt as opposed to the particle in a suspension to develop different coatings. Essentially, there's a lot to explore. We are mostly focusing on processing, but there's a lot to study and understand in the microstructure and the performance side of things. And we are very keen to work with anyone who is interested to use any of these coatings. Thank you very much for listening to me today.